Welcome, my friends! Today we will be discussing the binomial distribution. The binomial distribution is an extremely important and useful distribution that can be used to calculate probabilities under specific circumstances. There are four features of binomial experiments, which must all be true in order to use a binomial distribution. In a binomial experiment, there are a fixed number of trials where some outcome is observed. Each trial has only two outcomes, success and failure. The user decides which outcome counts as success and which outcome is failure. Each trial is independent, meaning that the outcome of one trial has no impact on the outcome of any other trial. Lastly, the probability of success is the same on each trial. The classic example of a binomial distribution is flipping a coin n times, let's say 10 times. Let's check the four conditions. Are there a fixed number of trials? Yes, there are. There are 10 flips on the coin, which make up our trials. Does each trial have two outcomes, success and failure? Yes, the only two outcomes when a coin is flipped are heads and tails. We might let heads represent success and tails represent failure. Is each trial independent? Yes, the outcome of one flip of the coin does not influence the outcome of any of the other flips. Is the probability of success the same on each trial? Yes, the probability of flipping heads is 50% on each flip, assuming that the coin is fair. As all four of the conditions are met, flipping a coin 10 times is an example of a binomial experiment, which can be modeled using a binomial distribution. Let's say we are drawing 3 balls from a bag with 5 green balls and 2 blue balls, without replacing each ball after it has been drawn. Can this situation be modeled by a binomial distribution? We must check the four conditions. Are there a fixed number of trials? Yes, there are. There are 3 balls that must be drawn, which represent the 3 trials. Does each trial have two outcomes, success and failure? Yes, we might let green represent success and blue represent failure, or the other way around. Even if we had more than 2 ball colors, we could still define one color as success and all of the other colors as failure. Is each trial independent? No. The outcome on each draw changes the makeup of the balls in the bag on subsequent draws. The outcome of each draw is dependent on the previous draw's outcome. Is the probability of success the same on each trial? No. The probability of drawing green is 5 out of 7 on the first draw, but the probability of drawing green on the second draw will be 4 out of 6 if green was drawn first, or 5 out of 6 if blue was drawn first. Since the probabilities change for each trial, we have not met the fourth condition. If any of the four conditions are violated, we can't use the binomial distribution. As 2 out of the 4 conditions have been violated, a binomial distribution cannot be used to model our example. Whenever you are working with a binomial distribution, you will need to define two numbers. N represents the number of trials, and P represents the probability of success. You can also define the probability of failure, Q, which can always be found by just taking 1 minus P, since P and Q are complements. The notation x tilde bin parentheses n comma p means that the random variable x follows a binomial distribution with n trials and probability of success p. If x represents the number of times heads is flipped in 10 coin flips, then we would say that x follows a binomial distribution with 10 trials and a probability of success of 0.5. For any binomial distribution, you can calculate the mean by multiplying n and p together, and you can find the standard deviation by taking the square root of n times p times q. In our example, when n was 10 and p was 0.5, the mean is 10 times 0.5, which is 5. For the standard deviation, remember that q is the probability of failure, which is 1 minus p, or 1 minus 0.5, which is, again, 0.5. So the standard deviation in our example is the square root of 10 times 0.5 times 0.5, which is about 1.58. Suppose it is known that about 23% of total deaths in America are from heart disease. let x represent the number of individuals out of a sample of 7 who will die from heart disease. We can quickly go through the conditions to verify that a binomial distribution is appropriate. Are there a fixed number of trials? Yes, there are. There are 7 trials, so n is equal to 7. Does each trial have 2 outcomes, success and failure? Yes. We can define success as an individual dying of heart disease and failure as an individual not dying of heart disease. Notice that success doesn't have to be something positive or good. It's typically just the outcome you are more interested in asking probability questions about, which is individuals who die of heart disease in our case. Is each trial independent? Yes. If the previous individual sampled ends up dying of heart disease, that doesn't impact the probability other individuals in our sample die from heart disease. Is the probability of success the same on each trial? Yes. The probability of success, dying of heart disease, is 0.23 in all trials, so p is equal to 0.23. All 4 conditions are met, so we can use a binomial distribution to model this example. We say x follows a binomial distribution with 7 trials and a probability of success of 0.23. The mean is n times p, or 7 times 0.23, which equals 1.61. On average, 1.61 individuals from a sample of size 7 will end up dying of heart disease. The standard deviation is the square root of 7 times 0.23 times 1 minus 0.23, since q is always 1 minus p. This simplifies to about 1.11. We can use the binomial distribution to answer a question such as this. What is the probability exactly 2 people from the sample end up dying of heart disease? This can be translated into the probability statement, the probability that x is equal to 2. Now, we can answer questions like these either with a formula or with a calculator. Some old-timers use probability tables, which we won't discuss here. Here's the big scary formula, which I won't discuss in detail. If you want to try to plug all the numbers into this formula, you will get this, which simplifies to 0.3007, or 30.07%. There is about a 3 in 10 chance that 2 out of the 7 individuals surveyed will die from heart disease. Due to the complexity of the formula, I tend to emphasize the calculator method of finding binomial probabilities. Let's take a look at the calculator to see how to find the probability there. Here I am with the TI-84 calculator. If you press second, then distribution, which is the second option in blue over the vars key, press up to get to the bottom of the list, and then you can continue going up until you get to the binomial PDF for binomial probability density function. You can select this option by pressing enter. The trials are just n, which is equal to 7, p is equal to 0.23, and x is equal to 2, since we wanted the probability that x is equal to 2. Now, if you have an older calculator, you won't get this menu that we're seeing here. Press paste, and here you'll be at the screen as it would look like on an older calculator, such as a TI-83. You simply need to put n, p, and x separated by commas, as you see here, if you have an older calculator that only gives you this menu. Press enter, and you will see that we get the same answer, about 30%. Now, you may have noticed a moment ago that there were 2 functions for the binomial distribution in the calculator, binom PDF and binom CDF. Binom PDF stands for binomial probability distribution function and calculates the probability x is equal to some value, like the probability x is equal to 2. The arguments n, p, and x are needed for this function. Binom CDF stands for binomial cumulative distribution function and calculates the probability x is less than or equal to some value, like the probability x is less than or equal to 2. This function also takes the arguments n, p, and x. The easiest way to see the difference between the 2 functions is to write out all of the possible outcomes for your experiment. In our case, we have the numbers 0 through 7. From a sample of 7 individuals, anywhere from 0 to 7 of them could die of heart disease. The binomial PDF function, the one that we just used, calculates the probability of one specific value for x, such as 0, 1, 2, 3, etc. The binomial CDF function, which we haven't used yet, calculates the probability of all values less than or equal to some value. So putting in 5 to the binomial CDF function gives the probability of anywhere from 0 to 5 individuals dying of heart disease. Or putting in 2 gives the probability of anywhere from 0 to 2 individuals dying of heart disease. You might be wondering, what if I don't want less than or equal to probabilities, and instead I want greater than probabilities? No problem. We can utilize the complement rule in that case. For example, if the CDF function with 2 plugged in gives us the probability of these values, we know that the complement is these values over here, greater than 2. We can always find the probability of the complement of an event by taking 1, which represents all of the outcomes, and subtracting off the outcomes that we don't want, less than or equal to 2. We'll look at an example with a calculator in just a moment. Recall our example where we were sampling 7 individuals and the probability that each individual would die of heart disease was 23%. Suppose we want to find the probability that at most 2 people from the sample will die of heart disease. On the number line, that's these outcomes, either 0, 1, or 2. We can write this probability as the probability x is less than or equal to 2. This translates into binomial CDF 7.232 in the calculator. We use the CDF since we want a less than or equal to probability. Otherwise, we would have to use the PDF function 3 times and add the 3 outcomes together, which is quite a bit more time consuming. In the calculator, we go again to second, distribution, arrow up until we get to binom CDF, and then we put in 7 trials, p is equal to 0.23, and x is equal to 2. This gives us 0.7967, or a 79.67% chance that at most 2 people die from heart disease out of a sample of size 7. Suppose we want to find the probability that less than 3 people from the sample die of heart disease. Looking at our number line, the numbers less than 3 would not include 3, but rather only the values smaller than 3. This is the same outcome that we had before, which could be written as the probability that x is less than 3. But this isn't very helpful for our CDF function, since the CDF function requires less than or equal to. The probability x is less than 3 is the same as the probability x is less than or equal to 2, which we already said could be modeled by binomial CDF 0.232, which is equal to about 0.7967. We prefer the second probability statement as it corresponds with the CDF function, whereas the first probability statement does not. So the moral of the story is to rewrite your probability statements with the less than or equal to signs for binomial probabilities, so that they correspond with the binomial CDF function. Okay, let's consider one more example. What is the probability that at least 5 individuals from our sample have heart disease? The phrase at least 5 includes any values that are 5 or greater, so 5, 6, or 7. This translates into the probability x is greater than or equal to 5. We can't use the CDF function directly in this case, since the CDF function only calculates less than or equal to probabilities. We will have to use the complement rule instead. 5, 6, and 7 are the outcomes we want, which means that 0 through 4 are the outcomes in the complement. We take 1, which represents all of the values, and subtract the complement, the values we don't want of 0 through 4, represented by the probability x is less than or equal to 4, to get our answer. This translates into 1 minus binomial CDF 7, 0.234, which is equal to 0.0088 when you plug it into the calculator. In the calculator, we first enter 1 minus, and then we go to second, distribution, arrow up to binomial CDF, 7 trials, p is equal to 0.23, and x is equal to 4, and then press enter. We get 0.0088, which is the probability that at least 5 individuals from the sample of 7 die of heart disease. Not very likely at all. Alright, my friends, we have finished our discussion of binomial distributions. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.